difference is relatively large. Namely, it is almost larger, except for this error term. It is almost larger than the distance between alpha and all its conjugates. So, and I mean this. So the minimum, so to speak, corresponds to the largest distance. So it's, I mean, if I make here a sort of a comment, let me sort of draw a picture. Let me try to draw a picture. So here we have maybe alpha. This is in some algebraic closure ES.
Yes.
And there's alpha. And then we have the conjugates of alpha. Maybe I actually, I'll do this later. So here we have alpha, and here we have the conjugates alpha prime, alpha, like this. And then maybe this one I want it to be. So the one which is furthest away is this alpha prime. And maybe I'll also.
Furthest point is alpha prime.
Alpha triple prime.
Triple prime. Okay.
Here. And so okay, so. Yeah. So this has largest distance.
By absolute value.
Yeah. I mean, largest right. I mean, largest distance for the absolute value. That means the minimum for the v function.
Right.
Yeah. Largest distance. Yeah, when I say distance, I really mean, so to speak, for the absolute value, multiplicatively.
Okay.
Largest distance to alpha. And this is alpha. This is alpha triple prime. And then there is kind of, I mean, the point is that we have another element which is maybe maybe closer, let's see, minus, so you take something. If it's really if it's right. And then there is, I mean, then there is a radius which is just a little bit larger. So this has, this, so to speak, this is positive. This is of radius alpha minus alpha triple prime
plus
times something like p to the power minus p over p minus 1 squared.
Yeah, right. That is the error term, right?
Right. So I mean, here the radius, I should have alpha minus alpha triple prime times p to the minus 1 p over p minus squared. So this is a little, and then the A is at least in here. Yeah.
But at least means A can be in the blue circle.
It could be even right. I mean, it could be even better than that. In which case, this inequality on the left, v alpha minus A is even greater than delta E of alpha.
Okay.
Yeah, right. I mean, in fact, yeah. So here, this distance, I mean, this radius here is the, I mean, this radius
alpha minus alpha triple
is precisely how do I want to I guess I just write alpha minus alpha triple prime, which is, so to speak, it depends on how we relate the absolute value and the valuation v, and I mean it's okay. I mean so this is somehow related to delta E of alpha. Yeah. Okay. So we can always approximate alpha by elements in E up to some. I mean, I mean somehow the delta of alpha gives us a measure on how close we can get to alpha. Roughly. Up to a little bit of an error. Okay.
Okay, and for point 2 is k bar and p bar representations of gk. So there are some notations. K is p-adic field, and there is OK, mk, and rest with k, summer k, and vk is the normalized valuation, and ek is vk of p, that is absolute ramification index of k over qp. Right? Then W is the ring of big vectors, so of k, small k, rest field, and k0 is the field of fraction of the W, so W attaching with 1 over p. So yeah, there is some example. So if k is qp, then W is gp, and k0 is also qp, and ek is 1. So I'm not familiar with the ring of big vectors, so
okay.
Yes, so I wrote some questions. So I think if k is degree 2 and ek is 1, then k0 is equal to k. Is it right?
Yeah. Yes. I mean, every time k0 is equal to k when k is unramified.
When k is unramified, k0 is equal to k.
No, sorry. W is W of k. No, sorry. No. When k is oh, right. So okay. When k is unramified, when k is unramified over qp, when k is unramified over qp, then k is k0. I mean k0 is when it says here, maybe that's right. I mean, well, I mean, we are not assuming, or do we assume that the residue field is finite?
Yeah, maybe because k is p-adic field, so local field. So I think the rest is the finite field.
Yeah, I mean, some would even consider something like QPNR or so, the completion of the maximal unramified extension as being a p-adic field. but it doesn't really matter that much. I mean, yeah, if k is if k is finite over qp, then k0 is the maximal unramified subextension. Yeah. Okay. This is just the same as adjoining. Basically, I mean, if the lowercase k, I mean, if say lowercase k is fq, then this k0 is just qp.
Yes, q minus 1. Okay.
So whenever k is unramified over qp, then k is k0.
So k0 is the maximal unramified extension, sub-extension in k. Over qp. Yeah, right. Okay.
Yes.
Okay. Okay, and then the third one is that C is the completion of the algebraic closure of k. V is 1 over ek vk. So that's satisfying. Vp is 1. And P0 is the ring or peak vector of the algebraic closure of k, small k, and the attaching with 1 over P. And I have one more question. So maximal unramified extension is unramified extension, right? So as I know, unramified extension is finite extension. No.
Well, I mean, one
in the definition.
One can also say, I'm not sure if I read. I mean, one can also say that basically we call an infinite degree extension unramified if any finite subextension is unramified.
So okay.
And why the maximal unramified extension is not complete? There was actually a homework problem.
Yeah.
About this, right? I mean, if you take a sequence of roots of unity, where the order of those roots of unity tends to infinity, and they are all co-prime. I mean, the orders are not divisible by p. And then you consider the series zeta n time. I mean, zeta n. Let's say zeta ni, or we can just. I mean, here's an example. I mean, this one, and you basically. I mean, this one. I mean, there are many more, but say zeta q to the n minus 1 times p to the n. I can start with 0, for instance, or maybe with 1. Yeah, I mean, this is an element of the maximal, of the completion of the maximal unramified extension, but it's not contained in. I remember it. Yeah. I mean, this is because if it were in the maximal unramified extension, it would be in some subfield. It would be itself algebraic over QP, but this one, as one can show, is not algebraic over QP. This one, it doesn't have a stabilizer. It doesn't have a stabilizer which is of finite index in the Galois group of k and r over k. Yeah. So, in fact, I think the stabilizer. I mean, this is the same by continuity as the Galois. The two fields have. So, I mean, well, this is not strictly. I mean, this is. I should rather here. I mean, this is not a Galois group, but this because this is not a. This is really a transcendental extension, but the automorphism group. I mean, we always mean continuous automorphisms. the continuous automorphisms of K and R hat are the same as the Galois automorphisms of K and R, and the stabilizer of this is, I think it's just one. It has a trivial stabilizer. Yeah, because in order for, I mean, somehow if you apply such an automorphism, you just need, I mean, by continuity, you just apply it to the coefficients. But the coefficients are roots of unity. So so the action on any coefficient is by sending this roots of unity to some other roots of unity.
Yes.
But then it can only be a root of unity of the same order. So it can only be a power of this. I mean, each coefficient can only be sent to some power of this one, where the exponent is co-prime to q to the n minus 1.
Right.
But then somehow, I mean, then by reducing modulo p square, and so on, or I mean, just I mean, you see, I mean, this is a unique expansion of an element in K and R hat. Every element in K and R hat. So for every psi in K and R hat, there exists a unique sequence Cm plus 1, and so on, where all coefficients are in mu. I'll write this union 0. So to speak, to the n is, so I mean there exists a unique sequence. Maybe I should write it. Cm plus 1 in mu. So the superscript p means roots of unity of order co-prime to p. So mu p. I mean, well, maybe I'll finish the statement first with the property that c is equal to, I mean there exists a unique m such that this is Cn p to the n from n equal m to infinity, where say, I mean, Cm is non-zero, and I mean, maybe here then we also exclude 0, and this mu superscript p is just all, well, zeta q to the n minus 1 to the k, where k is in z, and n is greater or equal to 1. So this is the same as the set of all roots of unity of order not divisible by p. And and therefore, because of the uniqueness, if a Galois automorphism stabilizes the c zeta of, I mean, this maybe c0 is psi 0 if and only if for all n greater or equal to 1, sigma of zeta q to the n minus 1 is sigma q to the n minus 1. But then sigma induces the identity on the residue field. But then, because in this case this is isomorphic to the Galois group of the residue field, sigma is the identity. And therefore this element, it cannot lie in any algebraic subextension. It is in fact transcendental. This is sort of, I mean, saying that it is not, I think that's pretty, I mean, this one Um, yeah, I think this already comes maybe as a, so every element which is algebraic over K and contained in this K and R hat is already in K and R.
Yeah.
And this element is then transcendental over K, in fact. This element is transcendental. Yeah.
And yeah, and P is P0K, so this is equal to the completion of K, the maximum unified extension of K. And for any subfield L of C, so we can also define OL and ML and the rest of the KL. And the L hat is just completion, p-adic completion, and satisfying the following. Yeah, OL hat is project limit, and L hat is just the field of fraction, and then KL hat is KL. And if L is finite extension of K0 inside K bar, let L0 is the vector of the ring of the vector of KL attaching 1 over P. And there is some facts. So yeah, K over K0 is totally lamified of degree EK, because I think K0 is the maximum subextension in K.
Right, which is unramified.
Unramified over K in K. And OK is also a free W module of length EK. So if there is uniformizer pi K, so the set can be a K0 basis of K or W basis over OK. And P0 and K are linearly disjoint over K0. So for example, if K is degree 2 p-adic local field and EK is 2, then K0 is QP and P0 is the completion of maximum unified extension of QP, and P is K and R hat, and they have the following diagram, right? So, and sigma be absolute Frobenius map on K0. Then if L is between K0 and K hat, then C invariant GL is equal to L hat. Yeah.
Okay. I see. The Galois invariance of GL in C. Okay.
And L hat is equal to L. If and only if L over K0 is finite extension. And we have, in fact, the exact sequence like this with the inertia subgroup and absolute Galois subgroup and Galois group of the rest of field. This exact sequence. And but I'm wondering why G P bar over P is equal to IK.
Okay. So, yeah, let's see if I can. It's somehow, I mean, the Galois group of Right. So maybe let's. I'm not sure if it's good. We could maybe try to prove this directly, but let me take a finite extension. Okay. So I take p. So p was k times p0, and p0 is also yeah. So p0 is k naught and r
completion,
yeah. And I guess okay, I'll try to maybe do this directly instead of passing through. Although I think, well, let's say, I mean, I think the following is true. So here we have a little lemma, which says that if L tilde over P naught, no, over P, over P is finite, maybe Galois, then there exists an L over K, which is finite Galois, with the property that L P naught is equal to, this was P, is equal to L tilde. I think I must say I don't quite see. I mean, I now have a little bit doubts that this is true, but I'll still I keep it here because I think it might be true, and if it's true, I think this would sort of offer a path to proving what we want to prove. But maybe we can actually, let's see. So I mean the Galois group. So the Galois group of K bar, I think that's somehow. So the Galois group of K bar over K and R. Right.
That is isomorphic to IK.
Right. So right. I mean, this is known. I mean, this is basically almost
right. Yeah.
Now I think this one, right, and I think this one is also isomorphic to the automorphism group of K bar hat over K and R hat. But it's not. This is P, right? Yeah. This is P. Yeah. Right. Yeah. So I mean, okay. So when I think when we don't need the lemma, I think the lemma is really superfluous. Let me then erase it.
Yeah. K
yeah.
and our head is P, right?
But here, yeah, and on the left side, I mean, P is this one, but it's also the same as
K and our head.
P is so K dot P naught, but P is also K and R head. So and I claim, I mean, that this is the same. So here we take first the algebraic closure and then we complete. But we know this one is algebraically closed.
Yeah, right.
Now, if I take okay, right. So I think this is also the same. This is also in fact the same as the Galois group of K N R hat. Yeah. Again, this is some sort of continuity argument. That this should be the same. I mean, by restricting I mean this one. Oops. Yeah. I'm trying to. I mean, so K N R head bar I claim is naturally contained in K bar head. Why? Well, just because this one contains K N
in our head.
Right. I mean, obviously.
Yeah, right.
Obviously, this contains K in our head, but it's algebraically closed.
Yeah,
but it's algebraically closed. So it contains this. I mean, this is not an isomorphism. Again, by some other similar argument that I mean, these are elements. I mean, there are certain. I mean, one can certainly construct elements that are in here which are not algebraic over here. And in a similar, in a different but similar way, which shows that that this extension here is not algebraic. And therefore it cannot. I mean, this map cannot be an isomorphism. But I think it is still true that the completion of this one is equals to this one. Yeah, I mean this one is dense. I mean, obviously it's still dense. I mean, because it contains K bar. Right. This one contains K bar. And because it contains K bar, it has dense image. And then I think we can conclude that this is the same as this one. And this is what you want to show.
Right.
So I mean, the map would be then that there's a restriction map here. Similarly, I mean, this isomorphism is obtained by, well, I mean, the way I think the way I prefer to think about it, this is by restriction. But again, this is an isomorphism. And similar here, this is by restriction, and again, it's an isomorphism by density. Yeah, and by the fact that any Galois automorphism here here in this group it extends by continuity to to this field.
Mm-hmm.
So yeah. Okay.
So for any finite extension L of K0, we can denote L superscript sig as L attaching with mu p infinity. So that is the union of L of mu p to the n. And that is the same with LK0 sig, and that is the subfield of K bar. And there is HL and board gamma L. Okay. And then I don't know exactly Kuma theory, so
I mean, usually I understand actually something slightly different when I hear Kuma theory. Maybe can be proved from the. For me, this is rather a kind of cyclotomic theory. This is sort of cyclotomic theory. Right? This is kind of obvious here. This map, this is canonical. This is just restricted.
Yeah, right.
That's just the restricted. And this map, the second map is just a map which
power of.
Right.
Yeah.
We send sigma to the an modulo p to the n, where sigma of zeta p to the n, and this can be any primitive root is zeta p to the n to the power an. And then this sequence of elements is naturally an invertible element in ZP. And the fact, and every automorphism and any such sigma is uniquely determined on all the action on those finite order roots, by its very definition, because this field. So it's clear this is injected. But the key is that the image is a subgroup of finite index.
Yeah, but why?
Why is that?
Yeah, why finite index?
This is. So the key point is here. Maybe we don't have time as we want to go over. The key point is to show that if it had infinite index, it should be easy to see. Because this gamma L is a profinite group, and this is a continuous map between such profinite groups, that its image should be closed. And I think in ZP or in ZP cross, an infinite index closed subgroup is actually the trivial group. An infinite index. Well, maybe not quite, but almost. The thing is that ZP cross is isomorphic to Z modulo P minus 1Z times ZP via some sort of logarithm. At least if P is not 2, and if P is 2, then there is another finite group, plus or minus 1 in here. In fact, so Z2 cross is isomorphic to Z modulo 2. times Z2. It's somehow so here A, this is plus or minus 1, goes to plus or minus 1 plus, in fact 5, 1 plus 4 to the power A. This converges. This one can show that this converges. And similarly here it's an A comma say K bar. I mean K bar is maybe not a good is so somehow maps to something like K is not good. Maybe B. B maps to zeta p minus 1 to the power B times 1 plus P to the power A. And then you can try to prove that a closed infinite index subgroup is finite. I believe so, and it comes essentially from here or from here, from these finite products.
But they cannot be finite, so.
Right.
Because gamma L is.
Right.
Yeah.
That would mean that L contains infinitely many p power roots. P power roots of unity of arbitrary order, and then it would not be a finite extension anymore. Yeah. So maybe we'll stop here. But yeah, very good. I think I already all my annotations are now saved. I saved already. Now they're saved.
Thank you.
Okay, let's continue.
Now I can see.
Good. Yeah.
We did this page and maybe page 3.
I see, and all this, yes. Yes, and here we talked about the difference between the completion of the maximal unramified extension and the maximal unramified extension. Okay. We actually did
third page. Yeah.
Yes.
But from last our meeting, I have one question.
Yes.
Yes, I wrote my question about density. So I'm wondering how does the density implies this isomorphism? If there is density, it always implies isomorphism.
So when we use here density, let me see. The density of the I see. It is exactly okay. Let me try to. You're right. I see. So it is this isomorphism. Okay.
And right isomorphism also.
And the right isomorphism. Yes, yeah. I see.
The map is from the density below that.
Okay, let's just look at the left isomorphism first.
Okay.
So if we have here an automorphism of this k bar hat over k and r hat.
But automorphism means continuous automorphism.
Yes. Yes. Yeah. I mean, yes. You're absolutely right. I mean, it should always mean continuous. Yeah. Somehow C for continuous. Yeah. Right. I mean, in this case, it is not automatic, of course, yes, because if you have a finite extension, then we know that the absolute value extends uniquely, and then and then any Galois, if we compose the absolute value, if we precompose it with a Galois automorphism, it must be the same absolute value because of the uniqueness. Right? If you look at our absolute value of sigma of A, absolute value of sigma of A is always giving you an absolute value on your field. If sigma is an automorph, if you have an absolute value and you look at the map which sends A to the absolute value of sigma of A, you get another absolute value. And because sigma, if sigma is an element of the Galois group over K, then this absolute value is equal to A maps to absolute value of A if A is in K. And therefore, this absolute value that you construct using sigma is a new absolute value, but it is also an extension of the old absolute value that you started with. And because the extension is unique, it must be the same. So this means the absolute value of sigma of A is always equal to the absolute value of A. And this proves, I mean, from this it is easy to see that sigma is continuous. So for a finite Galois extension of a complete field, any Galois automorphism is automatically continuous for the topology given by the absolute value. But here, this is not necessarily the case
because it is not a complete.
Yeah, but I mean because the completion of the algebraic closure is not a it's not an algebraic extension. Yeah, it is not an algebraic extension of the completion of. Yeah, I mean here on the right hand side. This is the algebraic closure of this field, right? I mean, so here, I mean, this one is the algebraic closure of this field, including this one. So this is therefore here also the absolute value on this K and R hat extends uniquely to an absolute value on the algebraic closure because it extends uniquely on any finite subextension. And then any automorphism here is automatically continuous. But this is not true here, yeah, because this one is not. But I think it is, yeah. So I mean, again, I mean, well, I should exit this. So we should continue this. Okay. So now, if we have a continuous automorphism there and we restrict it to K bar, and it is the identity, then it must be the identity because K bar is dense in K bar hat.
Yes.
Now the question is, why is it surjective? Yeah, I think by the surjectivity is that. So I mean, this map here is easily. I mean, by the argument that I just gave is injective. And so to speak, the other in the other direction, it is by extending continuously to. If you have basic, I mean, again, think what is this completion? It consists of Cauchy sequences.
Yeah.
Right.
Yeah.
And then if we take a Cauchy sequence and we apply a Galois automorphism to each individual number in this Cauchy sequence, to each individual element, we get again a Cauchy sequence. Yes. Because again, automorphisms in here are automatically continuous. But then it is clear how this automorphism extends to the completion. Namely just sort of we present an element in the completion as a Cauchy sequence and apply component wise. Yeah. And I think then it's clear that it is surjective. Yeah. So surjectivity by extending continuously. Yeah, sorry. And injectivity by density, by the density of K bar in K bar head.
Yes.
And now on the right hand side, on the right hand side this is also the case that here the field, this field here is naturally a subfield in here.
Right. We check the Latin.
Yeah, we because it's algebraically closed, and it does contain the completion of the algebraic of the maximal unramified extension. So and in particular, this one contains the algebraic closure of K itself. So this field here is dense in this field here, right. And then again, I think we can argue in exactly the same way. Injectivity by density and surjectivity by continuously extending.
Okay, but surjectivity is just by restriction or so.
Well, but in order to show that every element in here comes from an element in here, we need to know that we can extend it.
I see. Okay, and I have one more question.
Yeah.
I know that, but I want to make sure. So, like number 2 question. So, the algebraic closure of p-adic field is always QP bar, right?
Yes.
Yeah,
when we say p-adic field, you mean a finite extension of QP? Yes.
Yeah, but the algebraic closure of the infinite degree over QP may not be same with QP bar, right?
If this infinite degree extension is itself a union of finite extensions, then yes. Right? So, for instance, the algebraic closure of Q and R, the algebraic closure of the maximal unramified extension, is the same as the algebraic closure of QP. But the algebraic closure of the completion of the maximal unramified extension is not the same.
Okay.
Yeah, so here, for instance, K, this is somehow K and R head bar
is nothing.
Is strictly bigger than K bar, or even K is even. No, actually, it's strictly bigger than K bar. Okay. But they, but if you complete here the right hand side, if you complete now this one, then you are getting a field which contains this one.
Right, because we looked at
but they are not equal.
Yeah, right. Because
this one here is not complete.
Yeah.
And this is, So
Yeah. I see. Okay, and then we need to start with lemma for 11, maybe. So there exists an integer such that L seek over L adjoint with mu p to the n is totally identified, and hence the residue field is the finite extension of KL. And for m greater than or equal to n, L this field and L0 adjoint with mu p to the m are linearly disjoint over L0 mu p to the n, and hence that implies this equivalence. Yeah, and if L is equal to L0, then n is 0. And we know that there is canonical isomorphism, like the first line. So one can decompose the board gamma L into delta L times gamma L, where gamma L is subgroup of Fp cross and or F2, and gamma L is isomorphic to GP. So, but I wonder how can decompose like this.
Okay, let me see. So
is it because 1 plus p GP is isomorphic to GP?
Yes.
I see.
Yeah, or in the case p equal 2, 1 plus 4 z2 is isomorphic, right? So the logarithm is well defined, and it maps this one actually it might I mean, it maps it to a group isomorphic to Z2. Maybe it's actually 2 times Z2 that you get. I mean, you're definitely losing. It's not 4 times Z2 because of this 1/2. Or
maybe yes. I checked.
I think,
maybe
or is this? No, wait, but that 1/2. Yeah, no, it's x plus. So what is the No, I think it is. It is fine. No, the thing is just that one. I mean, if one would write here 1 plus 2 times Z2. This is the same as Z2. Right? Because Z2 cross. Z2 cross. So somehow, I mean, yeah, and I mean on. This is now that I think about, I mean, I think one would actually be fine if you have sort of x to the n over n, and if v2 of x is greater or equal to 1, isn't it? Yeah. So then clearly v2 of x to the n is n times. Let's say this is let's say. So I mean we are looking at something like -1 to the n minus 1 over n. This is of course irrelevant. This the sign and v2 v2 of x equal m, and that's a positive integer, and then v2 of x to the n is m times n, and v2 of n is actually n minus r. It doesn't go to 0. That's the point. It's still integral, but it doesn't. Yeah. So this is s2 of n. S2 of n is the sum of the digits in the p-adic expansion of n. Right. This is the sum of digits in p-adic expansion. And of course this number can be very small. For instance, if n itself is a power of 2, if n itself is a power of 2, and then if m is equal to 1, we see that somehow, even though this is always p-adically integral, it's actually always greater or equal to 1, but it doesn't go to 0. I mean, yeah. So I mean, in this case, v2 of x to the n over n, it can be sometimes equal to 1 if v2 of x is equal to 1, and if v2 of n is just n minus 1.
Right.
Which happens. Now, if n, namely, it happens exactly when n is a power of 2. So I mean, so this does not. I mean, obviously does not tend to infinity, but it has to tend to infinity in order to converge. So yeah. I mean, but once we have this, I think then we are good in the sense. I mean, so here, if we replace this 4 by 2, it doesn't work. But if we have the 4, I think, then I think it goes into 4 times here. If I mean, you can verify it, right? I think this will be always greater or equal to 2. I mean, for instance, if you look at the second term, it's x squared over 2. But if you then have something divisible, I mean, 4 squared over 2 is already 8.
Right.
So it is contained. So yeah, no, I mean, in this case, it will be greater or equal to 2 always. The terms in the logarithmic series. Yeah. So it's, which is of course itself isomorphic to z2.
Yeah.
Yeah. So does this help somehow? I think so. Gamma, the bold gamma L. The bold gamma L is the image, right? It's the image of gamma L in ZP cross.
Yes.
Yeah. So I mean, if you have a subgroup of ZP cross, it's kind of clear that it must be of finite index.
Yeah.
It must then be, I think it's also then clear, it must be a product group, because ZP cross is, I mean,
product group.
It decomposes as a product of a torsion subgroup and a free group. And I think then any subgroup must also decompose like this.
Yes. I see.
I mean, certainly, I mean, the situation is relatively easy to understand here if P is odd, because this has pro order P. I mean, this is pro P, and this is relatively prime to P. So I think then it's sort of clear. If you have here, this is a little tricky because this is pro 2. It's a projective limit of 2 torsion groups, and this is also 2 torsion. But this I mean, this group itself has no torsion.
No torsion. Yeah.
So I think I mean, I mean, it shouldn't be a difficult exercise. If you, so, I mean, give yourself the following situation. You have a group, a finite group, and ZP. Just a finite group and ZP. And now you have and then you look at the product group. Is it true that every, say, subgroup of finite index, even open, I mean, if you want, so it contains an open subgroup of the ZP, that it itself must be a product group with a subgroup of the first group and a subgroup of the second group, right? This is so to speak the question here. So the question is, if you have
product group.
Yeah, I mean here you have maybe
Toshan and Toshan free.
Yeah, I mean, so let me write it this way. I mean, it could even be more general. I mean, probably. So I mean, here you have a finite group, and you have the CP, and you have this, which is, say, open. In which case, it is automatically a finite index,
right.
Because this is compact on the right hand side. Then I think H. I mean, then there exists. Unfortunately, we have to go soon, but not yet. I mean, there exists some F prime, a subgroup in F, and some Z. Yeah. Such that H is equal to F prime
Z
times Z. Yeah, I think it's especially easy if you assume that F, that P does not divide the order of F. I think then one can easily see here. I mean, you could be thinking about something like you take -1. I mean, I think of this F2. I like to rather think of it as plus and -1. If you take an element of the form -1, comma, say 1 plus 4. And then you consider the smallest closed subgroup generated by this one. Does this really split as? Does it really split as? I mean, in the way we said. I mean, this is somehow apparently implied, or maybe we are in a slightly stronger situation. But I think if P is odd, everything is fine and no problem at all. And otherwise, do you see my point? For instance, if P is 2 and we consider 1, 5, the element 1, 5, and then we consider the subgroup generated by this, and we even take the closure. I mean, if this is a subgroup, I mean, this certainly is then an open subgroup also, and if it's of the form as we say, then it would have to be everything. But it's not quite clear how you would get. To me, at least, it's not quite clear how you get in this group the element -1, comma 1. But taking the closure. So because the first entry here, the first entry is -1. If it splits, like then you need to have an element. You need to have the element -1, comma 1 in there. And that's maybe not so obvious. Maybe we are in a somewhat stronger situation when P is 2. I now feel like that's maybe not quite, I mean, no, I mean, yeah, I know. I rather believe that if P is 2, there is that's actually maybe not true. For instance, you can take the subgroup, the diagonal subgroup, inside the diagonal subgroup. Maybe delta is not a good notation here, but I'll call it still delta for the moment. I call it D maybe. The diagonal in Z2 times Z2, so consisting of all elements x comma x. I mean, now if we I mean here I mean in the previous notation when I wrote -1, I rather think of this multiplicatively, of course, but if I think additively of it, it would be like 1. I mean, so I mean, if you look into here now you project this onto Z2 modulo 2Z2 times Z2. So in other words, in the first coordinate, you always just do modulo 2.
Right.
Then what you are getting is, I think, I mean, well, what you are then getting is some subgroup in here. And I don't see how this subgroup decomposes as a product of a subgroup in here and a subgroup in there, because in fact, I mean, I think it's clear. I mean, if you project onto Z, I mean Z mod 2, which is the same as Z2 modulo 2Z2, you get a surjection if you compose, I mean, from D, just because you have this, and if you project onto Z2, you also have a surjection.
Right.
But then, if the group in question decomposes as a product group, if the image decomposes as a product group, it would have to be everything. So I think that's, I mean, so I'm not saying it's not true, but it's not a purely group theoretic result. It might, I mean, it would have to have something to do with the fact that this bold gamma L is the image of a or is a Galois group. Is a Galois group. Is the Galois group of this L cyclic over L. I think the reason is probably the following. Yes. This is already well. Okay, well now I would have to think about it. I think we can just assume P odd or we just have to think a little bit why this should be true. But it's maybe it's I meanwhile I think this argument is correct in that it shows that it's not a purely group theoretic result. I also think, without going into details, that there's no problem when P is odd, for purely group theoretic reasons. Basically, because these guys have different orders, different pro orders. The first, then it shouldn't be a problem, I think. So here, then okay, I'll still, and then we have to go over. Sorry. So here, P does not divide the order of F. Right. Then I think should be true.
Like odd case.
Right. Yeah. This then always win. Okay. Yeah. We didn't. Okay. Well, we'll continue the next time. You won't have much to prepare because you have already another file prepared. So don't worry. Yeah.
But in the next note, I wrote the continuous cohomology and abelian and non-abelian cohomology. Because I didn't know that. But today you was saying about this.
Yeah. But I did not define it, right? But, Yeah, in fact, we will need the H1, the non-abelian H1 for this.
And there is the topic in the chapter 1. I studied.
See you